Hi and welcome back. So in the past video we began finally, I have been leading up to it for a while, we finally began talking about the F block electrons. And again, I do just want to say if this is confusing you, if you felt you understood all of the electron configurations for pretty much everything above the F block, and hopefully you're still you're not too confused by the F block. But I do just want to, I guess, let you know that essentially a General Chemistry 1 class, or at least my General Chemistry 1 class, we really didn't deal with the F block so much. So hopefully it's not confusing you, but if it is, don't really worry about it so much. Maybe look at some more videos on YouTube, and hopefully you'll and also definitely check out Wikipedia's page. I've got Wikipedia's page open right now. I'm definitely referring to this a lot. If you just do a Wikipedia search for periodic table, it's a really great resource, especially for doing these electron configurations. But anyway, what I'm actually going to essentially do in this video is I just want to show you which elements we kind of talked about a rule for figuring out electron configurations. So like I'll do one real quick, and I won't be able to pronounce this, but if we said we wanted to do an electron configuration for this element, for HO, I can't pronounce whatever that is, but if we were going to do this and we're going to use our nearest noble gas electron configuration that we've sort of used a little bit over the past couple of videos, what would our nearest noble, or our nearest previous noble gas be to HO? And remember that HO, it falls somewhere in here in the periodic table. So the nearest previous noble gas would be xenon. Right? So we would say that HO has the same electron configuration as xenon, and then on top of xenon we're going to add our 6s electrons, so we're going to add 6s2, and then we're going to add on, and hopefully you remember that this is going to be our 4f level, and this is going to be our 5f level, and just like we backfilled one orbital in our D block, we're going to backfill 2 levels of orbitals. So instead of being 6f, this is actually going to be 4f. It's going to be the 4f level that we're filling up. So, and hopefully you understood that. If you didn't, I'd say maybe watch. I think I introduced that maybe 4 videos ago. But so anyway, our electron configuration, we're going to have 4f. And then how many electrons are we going to need in this 4f orbital? Well, you can see I've numbered across the F block, so we could just count across, and we can see that HO is under our 11th place in the F block. So we are going to end up needing, sorry, I'm still maybe just a little sick, but anyway, we can count across, and we can see that that HO has got 11 electrons in this 4f orbital. And we can check that and say that xenon has got 54 electrons, plus 11 would be 65, plus 2 would be 67, and we can see that matches our number. So this equals 67 electrons, and that works out. So that is what the electron configuration is for this element HO. What I want to do in this video is I just want to point out all of the exceptions in the F block to this rule, I guess. So let me show you. The exceptions, they're going to be mainly at the beginning of the F block, and they're going to, so all of these elements that I've boxed in orange, so La, Ce, Ac, Th, Pa, U, and Np, these are all exceptions to the rule. And we'll just maybe spend a little bit of time. I'll just take you to the Wikipedia page, and we can look at what the electron configurations actually are for all of these elements. And then the two other exceptions, and these ones might be, sorry, these ones might be a bit easier to understand why they're exceptions, but I can't pronounce either of these. Or actually, no, is that Korea? Anyway, sorry. These GD and CM are also going to be exceptions, but it might be a little bit easier to understand why they're exceptions. Because keep in mind, our 4F level electrons, and we talked a little bit about this, and hopefully you understood this when we talked about this in relation to copper and chromium. So I'll just circle these, copper and chromium. But there's a certain amount of stability associated with having an exactly half-filled electron subshell, rather than having, one electron past a half-filled electron subshell. So essentially, these two elements, they're under our 8th position in our F block here, GD and CM. These are exceptions, and they're a bit more predictable why they are exceptions to our rule for electron configurations, because they're similar for the reasons that chromium and copper were exceptions to the electron configurations that we saw in our D block. And maybe I might talk a little bit. I'll probably talk much more about that further on in the future of this playlist. I don't think I'll go into too much depth on that right now. But anyway, I'll talk about that more in the future. Anyway, what I think it might be helpful to do is just, hopefully you've got a good idea of if we generalized a rule. So if we generalized a rule for figuring out these electron configurations in the F block, hopefully actually what I want to do now is just really go to Wikipedia and look at some of these exceptions and kind of, maybe not realize so much why they are exceptions, but just look at what the actual electron configurations are for these elements. So I'm going to go and get Wikipedia. And so let's start with the first one. Let's start with lanthanum. So we pull that up, scroll down to the electron configuration, and if we take a look at lanthanum, what would we expect? What would we expect for lanthanum's electron configuration? Well, we would expect this xenon. Let me just scroll down. We would expect xenon and then 6s2 4f1, right? That's what we would expect if we could generalize a rule about that. We would expect 6s2 4f1. But what do we actually get? Well, we get our 6s2 electrons, but we don't have any electrons in our f orbitals. All we have is we have one electron in our 5d orbitals. So that's kind of interesting, that we would maybe start filling up those 5d orbitals first. So that's our first exception. And you're going to see that lots of the other exceptions for these elements are going to look kind of like this. So let's look at, what is this, cerium. Let's look at cerium. And now we see there should be, I guess there doesn't really need to be the one superscript there, but we can see for cerium, what would we expect? Well, we would expect xenon 6s2 and then 4f2, right? But now what do we get? Well, we do get, and you can imagine there should be a 1 superscript above 4f there, and there should also be a 1 superscript above 5d there. But we have got 1 electron in our 4f orbital, and then also 1 electron in our 5d orbital. So, that's you could imagine that maybe this 5d, I think you don't have to imagine, I think it is this way, that our 5d orbital has got maybe a little bit lower energy. That electron is able to penetrate a little bit further into the nucleus, and hopefully, or further in towards the nucleus. And hopefully you understood that. If I'm confusing you by talking about that, let me know, and I'll maybe make a video explaining that last statement a bit more. But Anyway, we can at least see why I mainly want to, get across right here is that this element, this cerium, is an exception to our rule for electron configurations. Let's just look at a couple more of these. So, actinum. Actinum, again, it's a similar type of exception, right? Because what would we expect for actinum? Actinum is right here on our periodic table. And if we were doing nearest noble gas electron configuration, and actually, you know what? I'm going to erase this right here, because all the other electron configurations we're going to look at are going to be down in the second row of our F block. So there we go. Okay, so actinum. So if we're looking on this second row, our nearest noble gas to any element on this second row is going to be radon, right? It's going to be radon, which is right here. So we would say radon. And then for actinum, what would we expect here? And maybe I'll just write in, so all of these we're going to expect to have a 7s2. And then for all of these, we might expect, or we might see a 6d something. And then we also might see change colors, we also might see 5f something. And so for actinum, what would we expect? Well, we wouldn't expect any electrons in our d orbital, right? We would expect to find 7s2, 6d0, so no electrons in the 6d orbital, and then 5f1, right? But what do we get? We get no electrons. What we get is we get no electrons in our 5f orbital, and we get one electron in our 6d orbital. So that's what we get for actinum instead of I guess what we would expect. So actinum is going to be an exception to any rule that we generalize. How about how do you pronounce this? Thorium. Let's do thorium. And thorium is interesting too. So the nearest noble gas is going to be radon. And what would we expect for thorium? We would expect radon, 7s2, and then 5f2, right? But what do we get? Instead, we don't have any electrons in our 5f orbital. We have radon, 6d2, and then 7s2, okay? So thorium is also going to be an exception. Let's do the next one that I can't pronounce. Protec. I'm not even going to try. Sorry. Okay, so this one is also going to be an exception. So what would we expect for this? We would expect radon, 7s2, nothing in our 6d orbital, and then 5f3. That's what we would expect for this element Pa. But what do we actually get? Well, we get two electrons. We get two electrons in our 5f orbital, and we get one electron in our 6d orbital. So again, we're not necessarily we haven't, I guess, shed our habit of having electrons going into our 6d orbital, or however you want to think of that. We're still electrons are still going into our 6d orbital before they're I guess willing to fill up our 5f orbital. So you can see that because of that, this element Pa is going to be an exception. Let's go on to the next one. Let's go on to uranium. I think we might have already done in a past video, but we can just take another look and see that what we would expect for uranium. What would we expect? We would expect uranium is right here. We would expect radon, 7s2, 5f4, right? And what we actually get is 5f3, 6d1 in addition to our 7s2. So, you can see that this is a little bit of an exception. So anyway, I'm actually going to stop the video there. We went through most of our exceptions. We actually had 3 more to do, but maybe you can do those on your own and think about. And also, at some point in these videos, I am going to talk more about why these 2 elements are exceptions, because they are exceptions very much like copper and chromium, or for you could say the similar reasons why copper and chromium were exceptions in our D block. And maybe I will talk about that more in the future, towards the end of the playlist. For right now, I think I'm going to leave you there, and maybe you can ponder on your own. Why do you think these 2 elements, GD and CM, are going to be exceptions? And you can look up the electron configurations for these 2 elements and think about, well, why are these 2 elements going to be exceptions? So anyway, I'll actually leave you there. Yeah, my phone's ringing. I'll actually leave you there, and in the next video, or next bunch of videos, we're actually going to start talking about, so far with all of these electron configurations, and really with everything we've been doing in this playlist, we've been talking about all of these elements as being neutral. So we've been saying that all of these elements have the same number of protons as they do electrons. And you remember that our proton was positive, and our electron, my computer's starting to act up, our electron was negative, if you remember that. And so far we've been talking about all of our atoms that we've been looking at electron configurations for, all having the same number of protons and electrons. And what we're going to start talking about over the next bunch of videos are cases where we don't have the same number of protons and electrons. And you can maybe start thinking about what that means and what our atoms might look like. So anyway, thanks so much for watching, and I'll see you in a future video.